Now, following up on the previous video lecture, in this video lecture we'll consider a particular type of measurable functions which are called the extended Borel functions. We'll start with the definition of extended Borel functions and establish some criterion for when a function is an extended Borel function, and another criterion also to understand the pullback of Borel sets. So let us start with the definition. A Borel function is just a function, a measurable function that goes from a certain measurable space, which is a sample space with a sigma algebra, to the real line with the Borel sets. And an extended Borel functions, and we'll make more emphasis on extended Borel functions than Borel functions. An extended Borel functions is nothing but a measurable function whose target space is the extended real line with the Borel sets of the extended real line. And this is the reason why we'll focus on extended Borel functions in this module, and the reason is the following. Every property of extended Borel function will also hold for Borel functions. And we can think of Borel functions as simply an extended Borel function that never takes the infinite values. Now let us state some simple criterion that we can test in order to say that a certain function taking values on the extended real line is measurable. And the lemma of equivalent criteria, the lemma says we can choose one of these four conditions to check in order to say that a given function is measurable. So an extended Borel function, so a function taking values on the extended real line, it is an extended Borel function if and only if any of these conditions occur. So in order to check that it's an extended Borel functions, it is more convenient to check either one of these conditions. Once we have checked it, the most convenient formulation to use out of these five is of course the first one, because it is a much stronger property to be an extended Borel function, because that means we can replace this set by any set in the Borel sigma algebra B of R extended. In order to prove the previous lemma, let's recall the main result from the previous video lecture, which is that in order to check that a function is measurable, it is enough to check that the pre-image of sets are in the sigma algebra of the source space only for sets in a generating class. So it's enough to take a class whose generated sigma algebra is the sigma algebra of the target space. We don't need to check this condition for every set in the sigma algebra of the target space. And second, let us recall this, it was given as an exercise on chapter 2 of the lecture notes, that for the Borel sets of the extended real lines, they are generated by infinite intervals that include infinity and which end at any point A, any finite point A, and is open, or that it's closed, or sets that start at a point A, closed at A, and go up to plus infinity including infinity, or open at A, ends at infinity, closed at infinity. Any of these and many more different families of sets, they all generate the Borel sets on the extended real line. So if these two key facts that we have recalled, we're going to prove, let us go back, we're going to prove this lemma here, which says that we can check either of these conditions in order to conclude that f is an extended Borel function. And now in order to prove the lemma, well, let's prove the equivalence that f is an extended Borel function if and only if the pre-image of of this closed interval that includes minus infinity, that this pre-image is in F1 for every A, for every finite A. So let me write here real A. And what does it mean? What is the pre-image of minus infinity A? This is the set of all little omegas such that f of omega is in this interval, which we are writing for very short notation as simply f less than or equal to A here. So let us go back 2 slides. This f less than or equal to A here, which I'm copying here, it means really just the condition that the f of omega is less than or equal to A, which is the pre-image of this closed interval. And now, how can we conclude that these two conditions are equivalent? Well, we go back 1 slide and we see this lemma here, which says this class generates all the Borel sets of the extended real line, and when we have a class that generates all the sets of all the sigma algebra of the target space, then it is enough to check that the pre-image of those sets in that class generate, they are all in the sigma algebra of the source space. And this is exactly what we have here, so those two previous lemmas that we recalled, they match perfectly to give this equivalence. And using an identical argument, we can prove that this is equivalent to f minus 1 of minus infinity A open at A is in F1 for every finite A, etc. So we can prove the other 4 equivalences to analogous conditions to conclude the proof of the lemma.